Welcome back to the second video for Tech 259 for Monday, April 5th. In this video, we're going to talk about DC generators and how we can design a device that produces a solid, consistent DC voltage instead of our sine wave voltage that we've talked about in our generators so far. But before we do that, there's one thing I want to show you real quick. I had a bit of a throwback memory as I was thinking about this topic, and I was remembering the way I talked about this topic 1 year ago. And of course, it was one of the first videos that I made when we were stuck at home, when we were in shutdown. So I wasn't even allowed to come to Turner Hall. And so I was teaching about generators and things like this that we're talking about right now from my basement in my home. And I was reminded that one of the best examples, I think, of something that we talked about last week, Lenz's law. We talked about that last week. And I think one of the best examples that I can think of about Lenz's law is actually spinner bike, like exercise bikes, spinner exercise bikes. And I actually have one of these in my basement. So I used that to explain Lenz's law last year. And I think it actually was pretty interesting to think about. So before I move on to DC generators, I think I might actually just splice in a little video, just a couple of minutes from what I showed last year about Lenz's law, because I think it might be interesting. Good morning and welcome to Tech 259 for Monday, April 6th. Today we're going to talk about some review problems, and then we're going to talk about some interesting applications of generator theory. But first, you might be wondering, why am I writing an exercise bike? And the reason for that is because this actually provides a very good example of something that we talked about last time in our last class. So for most exercise spin bikes, the way that the resistance works is by controlling the knob. You tighten down a brake pad on the wheel that's spinning around. As you tighten it down, the friction becomes larger and larger, and so the resistance becomes larger and larger. But a lot of new spin bikes, and I actually just bought this a month or two ago because I was having some problems with my hip that wouldn't allow me to run on a treadmill. A lot of the newer spin bikes use something totally different that I think is really interesting. So let me show you a little bit closer. So there is no brake pad on this spin bike. Instead, all there is a metal wheel and there is a magnetic field. So right up here, there is a bunch of magnets. And as I twist this knob, it moves the magnets closer to or farther away from the metal wheel. And so if you think about what we have here, we have a piece of metal, which is conductive, and we have a magnetic field, and as I rotate this, we have relative motion between the magnetic field and the conductor. And so by those requirements, we know that we have an induced voltage because we meet the requirements for generator action. So we meet the requirements for generator action inside this metal wheel, but the question then is, so where's the current gonna flow once it's inside this wheel? We don't know where the current's gonna flow. And that's where Lenz's law comes in. If you remember, we talked about Lenz's law last time. And what Lenz's law says is that the direction that current is flowing inside this wheel, and remember the current flows because of the induced voltage. So the direction that the voltage will be induced will cause a current to flow inside here such that the magnetic field created by that flowing current inside this metal wheel will oppose the initial changing magnetic field. So the initial magnetic field that we have up here, and it's changing because we have rotation. That's what causes our changing magnetic field. So we feel that as resistance. And as I tighten this down, the magnetic field gets closer and closer to the spinning wheel, and it feels that as a stronger and stronger magnetic field. And so we get a larger and larger induced voltage, which creates a larger and larger current flowing inside this metallic wheel. And the direction of current flowing inside this wheel acts to oppose the magnetic field. So I feel that as more and more resistance, a stronger and stronger magnetic field that's resisting this magnetic field. So I feel that as the bike gets harder and harder and harder to pedal, as I crank this knob down and the magnetic field gets closer and closer to the metal wheel. So I think that is a pretty cool example of Lenz's law. I had to show you that as a real world example of Lenz's law. All right, I think that's one of the most tangible examples of Lenz's law that I can think of. So just wanted to show you that, and also kind of reminisce about where we were a year ago. Reminisce is probably not the right word, but you know, we're making progress, and vaccinations are on the way. So I'm glad we're where we are now and not where we were a year ago. So anyway, that wasn't directly applicable to DC generators, although it's actually applicable to all generators. So it's applicable, Lenz's law is applicable to AC generators as well as DC generators. So it is actually applicable to what we're talking about today. But today we are going to take our basic AC generator design that we've been talking about, and we want to modify it to create a solid, consistent DC output voltage. So remember, your AC voltage output kind of goes in a sinusoid, goes up for half a cycle, and then down to the horizontal axis, 0 volts, then to the negative half cycle, to a negative maximum, and then back up to 0, and then a positive half cycle, negative half cycle, and on and on and on. And as you're imagining that, keep in mind our basic design of an AC generator. The most fundamental design of AC generator has a coil of wire on the rotor. So remember that coil of wire, the armature on the rotor, and it's spinning around. And around the outside of the machine, we have our stationary, on the stator, stationary magnetic field. Imagine they're permanent magnets. They don't always have to be permanent magnets, but for right now, let's keep in mind our basic AC generator design with the armature on the rotor spinning around and the magnetic field on the stator, stationary magnetic field. So we're going to take that basic design, which produces an AC voltage as the rotor rotates, and we're going to make some modifications to it to produce something close to approximating a solid, consistent DC output voltage. So that's what we want to get to today. So keep that in mind. And now I'll go ahead and switch over to my slides, and we'll talk about how we can get there. All right, this is where we left off last time. So we're going to start talking about DC generators. First of all, just a little reminder or refresher of terminology, because I know a lot of this terminology is kind of new for most people. So let's refresh our memories. We can talk about the mechanical or physical components of a generator, and we can talk about the electrical components of the generator. Physically or mechanically, we've got something that is stationary, and we've got something that is rotating. And the part that is rotating we call the rotor, and the part that is stationary we call the stator. And normally, not necessarily always, but normally the rotor is rotating inside the stator. The stator is around the outside and it's not moving, and the rotor is on the inside and it's moving. All right, so those are our physical or mechanical terms. Our electrical terms, we have an armature. An armature is our coil of wire where we are inducing the voltage, and the field is the magnetic field that is required for generator action. All right, so our prototypical kind of basic generator, that's the easiest one to visualize, has a magnetic field on the stator, and it has the armature on the rotor. And the armature on the rotor is spinning around, and then in order to get the voltage from the armature, off of the armature and onto the electric grid where we can use it, which is stationary, we have to use slip rings. For the case of an AC generator, we use slip rings, all right? And then with the slip rings, which are directly connected to the armature, and the slip rings are rotating around, we have brushes that are riding on the slip rings, and those brushes conduct the electricity from the slip rings to the stationary electric grid, right? All right, so that's our basic generator. But we also talked last time about a couple different modifications. You don't have to have the armature on the rotor. In fact, there are some pretty good reasons for having the armature on the stator. Because if you have the armature on the stator, remember we showed some pictures of this. If you have the armature on the stator, that means your coils of wires are stationary and you don't need to use slip rings or brushes. All right. The downside with that is that, well, if you use a permanent magnet on the rotor to provide the magnetic field, then you have no control over the magnitude of that magnetic field. You can't change the magnetic field of a permanent magnet. All right, so that's a downside to that design with the armature on the stator. Or another design, which is actually very, very common actually for real generators, is to have the armature on the stator, and then on the rotor you have your magnetic field, but you use an electromagnet on the rotor. All right, now you're using an electromagnet to provide the magnetic field on the rotor, but if you're going to have an electromagnet on the rotor, then you got to provide electricity to that to get current to flow through that electromagnet on the rotor. And if you're going to have current flowing onto the rotor, now you got to use slip rings and brushes again. So there's not a perfect solution. There's a lot of different possible solutions. And a really common one, I would say the most common one in the electrical generator industry, is the one I just described, which is to have the armature on the stator, a three-phase armature, in fact, phase A, phase B, phase C, the three sets of windings on the armature, one set of windings for each phase. And then on the rotor, you have your magnetic field, and it's actually most common to use an electromagnet on the rotor for the magnetic field. And so you do actually have brushes and slip rings to send current to the electromagnet on the rotor. But like I said last time, that's still a better design than putting the armature on the rotor, because it takes less current to energize the electromagnet on the rotor than it would to take the current from the armature. If it was on the rotor, to take all that current from the armature, that requires some pretty significant large brushes and slip rings. So, and again, we don't like brushes and slip rings. We try to get away from them as much as we possibly can, because they require maintenance and replacement every once in a while. You got to shut down the machine to replace the brushes, and it's just kind of a pain in the butt. So if you can get away with it, you'd rather not use brushes if possible. All right, so that was a little bit of a recap of what we talked about last time, but I know that's kind of a conceptually challenging thing to think about, so that's why I just did a little refresher there. All right, but what I want to make sure you understand for right now is that we have mechanical terms, the stator and the rotor, and we have our electrical terms, the armature and the field. And it would be possible to have the armature on either the stator or the rotor, and it would be possible to have the magnetic field on either the stator or the rotor. All right. All right, so let's go ahead and keep going. And for right now, I want you to visualize our basic prototypical generator. This is an AC generator, which had our armature on the rotor. So our armature is spinning around here inside the magnetic field, and the magnetic field is on a stator. It's stationary. And this is a simple two-pole magnetic field, and that works for what we're talking about right now. All right, so the important thing that I want you to look at right now are these slip rings. All right, so this side of the armature goes through this slip ring, but doesn't touch this slip ring. Just goes through it and is attached to this slip ring. And this slip ring is rotating around with the armature. And then this brush, which is usually made out of like a carbon, like briquette type. It looks like a charcoal briquette. That's usually what brushes actually look like in the real world. And they just ride on that slip ring as it's rotating around. And then same thing for this side of the armature. We have this side connected to this slip ring, so it's rotating around with this side of the armature, and riding on it is this brush. And then the brushes are connected to wires, which connect to the electrical grid, which in this case is just represented by this resistor right here. All right. So this is our AC generator. What can we do to this design to start to turn it into a DC generator? All right, so remember the output from this AC generator, it looks like a sinusoid. It looks like this. It goes up and then down, and then up and then down. It's positive, then it's negative, then it's positive, then it's negative. All right, so a first step that we could do to get towards a solid, consistent DC output is, can we at least get all of our output voltage to be positive? It may not be consistent, it may not be a steady, consistent DC voltage, but can we at least get our output voltage to be positive and never negative? All right. It turns out you can actually. What you have to do is you replace these slip rings right here and here with something called a split ring commutator. Split ring commutator. What that looks like, I think the best picture is actually up here. All right, so remember before we had one side of the armature connected to one slip ring and a brush riding on that, and the other side of the armature was riding on a different slip ring and a brush was riding on that. But now instead what we have is this side of the armature permanently connected, like soldered, to this side of the split ring commutator, and this side of the armature is permanently connected, like soldered, to this side of the split ring commutator. All right, and these brushes are still stationary. They don't move, but the split ring commutator rotates inside there, rotates inside the brushes, all right? And the brushes ride along on the split ring commutator. So what's gonna happen is, let's say right now, it's not drawing the rest of the generator, but let's say right now from this, this generator, we're producing a positive voltage. And now what's gonna happen is the armature rotates half a turn, right? And remember, when the armature rotates half a turn, if it was an AC generator, then it would be producing a negative voltage. But what's gonna happen is, if this rotates half a turn, now this side of the armature is actually going to be connected to the other side of the split ring commutator, the other brush, right? And this side of the armature is going to be rotated and it's going to connect to this brush. All right, so in half of a rotation of the armature, the output of an AC generator would flip. It would go from positive to negative. But what we're doing here in the split ring commutator, we are actually inverting the polarity of the output every half rotation of the rotor. In this case, the armature is on the rotor. All right, so we're taking that AC waveform, positive, negative, and every half cycle, every half rotation, we are inverting the polarity of the output. So now instead of going positive, negative, it's going to go positive, and then instead of going negative, it's going to go back up positive again. And then instead of going negative, it's going to go positive again. So it's going to look like this. It's going to go whoop, 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 like that. So it's going to be something that looks like only the positive half cycle of the AC generator. And we have a name for that. We call that rectified AC. It's rectified AC. It's not really DC, because DC refers to a consistent, solid, steady DC output voltage, a positive output voltage. But this is not that. This is a rectified AC. So it's just going like this. It's never going into the negative voltage region. All right, so that's what a split ring commutator does. A split ring commutator inverts the polarity of the output every half rotation of the rotor. And here's another view. It's like a top view of a split ring commutator where this is a brush, and then as the split ring commutator rotates with the armature, as it rotates, then every half rotation, the split ring commutator is going to alternate which brush it's connected to. And one half of the rotation, this split ring commutator segment is connected to this brush, and then as it rotates half a turn, this section of split ring commutator is going to be connected to this brush as it rotates. All right, so hopefully that makes sense. That's what a split ring commutator does. It inverts the polarity of the output of the machine every half rotation of the rotor. So if our output did look like a sinusoid, then now it's going to look like rectified AC. So it never goes negative. It's always a positive voltage. It's not a smooth, consistent, steady positive voltage, but it's at least a positive voltage. All right, so that's step one. That is the first thing that you have to do to make a DC generator from an AC generator. Replace the slip rings with a split ring commutator. Here's another picture of that. Here's our armature that's rotating around. And you can see this side of the armature is connected to this side of this segment of the split ring commutator. And this side of the armature is connected to this segment of the split ring commutator. That split ring commutator rotates around with the armature. So right now, this side of the armature is connected through the split ring commutator to this brush. But as it rotates in half a turn, this side of the split ring commutator is going to be connected again through this segment of the split ring commutator, but it will have rotated, and now it's connected to this brush. All right, so that's what it's doing. Where you would have had a negative voltage down here, instead you keep a positive voltage. Okay. All right, so we have rectified AC. And it actually turns out for some applications, this is okay. This works well enough. One application I can think of would be a DC motor. This would actually work to power a DC motor because DC motors are frankly pretty dumb. They don't actually need a consistent, steady DC voltage to work. As long as you give them a positive voltage, they are going to create a torque, and that will create a rotation of the DC motor. I'm just giving you an example. For some applications, this rectified AC would actually be fine. It would work. But for a lot of other applications, basically anything involving electronics with transistors or solid state devices, modern computers or anything like that, you would want a smoother, steadier DC voltage. So how do you do that? It might not be obvious. This took a long time for people to develop, but eventually people did figure this out. What you do is you add another coil to the armature. So now instead of just having this horizontal coil connected to two segments on a split ring commutator, now what we do is we add another coil to the armature. So we have a whole second coil of wire on the armature. And now that second coil of wire is connected to two additional segments on the split ring commutator. So now we have 4 segments on the split ring commutator, each about a quarter of the length of the split ring commutator, a quarter of a circle. All right, so this side of the horizontal coil is connected to this part of the split ring commutator. This side, that's the top side of the vertical coil, is connected to the top segment of the split ring commutator. This side is connected to this part of the split ring commutator on the right, and this bottom section of this coil is connected to the bottom quarter of the split ring commutator. So what's going to happen now, every quarter of a turn of the armature, my brushes are going to switch which section. The brushes are stationary, but the split ring commutator is going to rotate with the armature. And every quarter of a rotation, we're changing which set of wires on the armature we are pulling the voltage from. All right, so now instead of going all the way down to the horizontal 0 voltage axis, now what's going to happen is the output looks kind of like this. So we're going to take the output from whichever set of coils on the armature is at that time producing the highest voltage. All right, so it's not going to be a completely steady, consistent DC voltage. It's still going to have some bumps in it, but it's going to be a lot better than rectified AC. All right, does that make sense? So every time we add a coil on the armature, we add another coil on the armature, we have to add 2 more segments to the split ring commutator. So as we go from one coil with 2 wires coming out of it to 2 coils, like is shown here, with 4 wires coming out of it, now we're going to go from a split ring commutator with 2 segments on it to a split ring commutator with 4 segments on it. And each segment is 1/4 of the full circle of the split ring commutator. All right, so eventually what we're going to do is we're going to keep on adding more and more coils to the armature, and we're going to keep on adding more and more segments to the split ring commutator. All right, so in the real world, in real DC generators, and they exist, they're not as common as AC generators, but they definitely do exist. In real DC generators, you can have hundreds of sets of coils on the armature. That's what this is right here. And remember, for every coil of wire on the armature, you add 2 segments to the split ring commutator. And that's what this is right here. This back here is the split ring commutator with many, many, many segments to the split ring commutator. And this doesn't show the brushes, but they would be back here. The brushes would be back here, riding on that split ring commutator and changing sections that they're connected to on the split ring commutator as that whole rotor is rotating around. All right. Here are some smaller examples. These are some smaller examples of DC generators. Here is the armature. So this is where we have a bunch of coils of wire, and here is the split ring commutator. So for each coil of wire here, we have 2 sections on the split ring commutator. Same thing here. This is the rotor of a DC generator. Here's the armature section right here with the coils of wire. And then you can see the wires are connected to the sections of the split ring commutator. The brushes will then just ride on that split ring commutator as it's rotating around. All right, once again, I know this can be confusing, so this is why I've talked about this several times. The stator is stationary, the rotor is what's rotating. The armature is where you are inducing the voltage. That's the coil of wire. The field is what's providing the magnetic field. All right, and once again, it's possible in most designs, it's possible to have the armature on either the stator or the rotor, and it's possible to have the field on the stator or the rotor. The vast majority, however, of DC generators, I will say, because they are using that split ring commutator, the vast majority of DC generators will have the armature on the rotor. And that way they can use the split ring commutator, and those brushes are riding on that split ring commutator. All right. All right, so that's going to wrap things up for the DC generator presentation. What I'd like to do now is show you a couple of examples that might make a little more sense now. So first of all, I'm going to show you this machine. I already showed this to you before last time, but I think it might make a little more sense now when I show it to you. So when we talked about it before, I showed you that we have an armature. Right, here's our armature. And by the way, I didn't say this before, but it kind of looks like it's 2 coils of wire on the armature, but it's really just one. These 2 coils of wire are connected. So it's really just 1 coil of wire on the armature. And we have our magnetic field, and we have our material of steel right here that has a high magnetic permeability. So this whole side is the North Pole, and this whole side is the South Pole. So this is a 2-pole generator. We have an armature inside here, and as I rotate this, the armature rotates around. And what I want to focus on right now is the slip rings and the split ring commutator. This is a pretty clever design. It's really kind of neat, whoever came up with this. And what's kind of neat about it is that you can move these brushes, and this can actually function like either a set of slip rings or a split ring commutator. Let me rotate this around. Keep your eye on this component right here, and you'll see how the design looks. All right, so you see how it's kind of split into 2 in kind of a strange way. And the way that it is designed, you can actually make this work like an AC generator. And if you want to make it work as an AC generator, then you put one brush all the way on one side, say over here, and now it's going to rotate around. And you put the other brush all the way on the other side, so over on here. So I'm going to move this again so you can see what's going on. So if I have one brush all the way over on this side of the device, and the other brush is all the way over on this side, notice that this brush is always connected to the same side of this device. So it functions like a slip ring. And this other brush would be over here, and it's always connected to the other side of this output device. So if I had one brush over here, say the bottom brush is over here, and the other brush is over here, then this would function like an AC generator because this is functioning like a set of slip rings, all right? But if I put the brushes in the middle, like right here, then what's going to happen is as this rotates, it changes which side the brush is connected to. So right here, it's connected to one side of the split ring commutator, and as it rotates, it changes which section it's connected to. So if I have the brushes in the middle of this device, like right there, then it would function like a DC generator because this is functioning like a split ring commutator. So that's a pretty cool design. You don't see that with larger machines just because larger machines are designed specifically to be either AC generators or DC generators. But this little hand crank generator, it's pretty cool that it can function as either an AC generator or a DC generator. Basically by changing whether this functions as a set of slip rings or a split ring commutator. All right, and then the brushes are connected to this rod right here, and that's connected to this wire, and so then here are the outputs from the machine. Whether it's an AC generator or a DC generator, either way, you take the output from here. All right, I'm going to show you a couple of other examples of DC machines, but let me switch over to the document cam to do that. All right, so here's a couple of examples. I'll show you this one first. All right, so here's one example, and I have to admit first, I'm actually telling you a little white lie. Actually, this probably was not designed as a DC generator. It was probably designed as a DC motor, but as it turns out, it doesn't matter. If it is designed to work as a DC motor, then it will also work. I promise you, it will work as a DC generator. And you can see a lot of the things that we've talked about. Here's the armature. So it's got a bunch of different coils on the armature, all physically rotated a little bit from one another. I haven't counted these. It's probably about a dozen. Probably got about a dozen. Sorry, I hope you could see that as I was talking about it. Probably got about a dozen sections of coil on the armature. And then we move this and we can see the wires that are connected from those coils. They're connected to these sections of the split ring commutator. So here are the sections of the split ring commutator. The brushes would ride along, just like my finger is. The brushes would ride along, and of course there'd be two of them. So the brushes would ride along kind of like this inside the machine. This is just a bearing to allow this to spin around. And then this is like a spline connection, and probably this was designed to be an output because, like I said, this was probably designed as a motor, probably for like a, it could be like the motor for a drill. It might be a little bit, maybe like a drill press. It might be a little bit too big to really be for like a handheld power drill. But maybe like a drill press. That's maybe my best guess. So anyway, so that's like the output spline. So that's like the output that's driving the drill bit or whatever it is. That's driving the load. Alternatively, this could be a generator, in which case this would be the input. So you'd have the input from, say, a turbine, I guess, or whatever is providing the rotational input, and it's rotating it. And so it's rotating this armature, and you've got a voltage induced in the armature, and then the output is from the brushes that ride along here on the split ring commutator. And the last part is the magnetic field. So in this case, it's two permanent magnets, and it looks like they're probably glued in here. And one side is going to be the North Pole, and one side is the South Pole. I don't know which. I'd have to take a bar magnet to figure out which one was which, but it doesn't matter. This rides along inside here, and it rotates like this. It's kind of squeaky because it's not right in the middle, so it's kind of rubbing along. It's rubbing on the permanent magnets, but if it was really in the machine, it wouldn't be rubbing, so it wouldn't be making those squeaking noises. It would just be rotating around like that. That's really kind of an unpleasant noise. All right, here's another one that's really very similar. This is a little bit smaller, so this could actually, I think that there actually is probably a good chance this could be actually from a drill, like a handheld power drill. So once again, we've got the armature right here, the sections of wire on the armature, and then those are connected to the split ring commutator. Here are the sections of the split ring commutator. And then the output is over here. Once again, I got a spline connection right there. This also happens to have a fan. This is not totally necessary, but it's probably just on here for cooling because it probably could get pretty hot as it's rotating. So this might rotate around like this, and that would draw cooling to cool the sections of wire on the armature. All right, hopefully it was helpful to see those real world examples. I know I always think it's nice to see the real world examples, the applications of how they're actually used in practice, not just in theory. So I try to give you that whenever I possibly can. So that is actually going to wrap up our discussion of DC generators. In the grand scheme of this class, DC generators are a little bit of an aside. I mean, they're important, but they're not nearly as common as AC generators because we know that what's on the electric grid, it's AC electricity. So we know that AC generators are more important and more common for practical purposes. But nevertheless, DC generators, they're still important, and there's only a couple of modifications that we have to make to our generator to turn it from an AC generator into a DC generator. So hopefully you can describe those now. So in our next class session, we're going to go back to talking about AC generators, but we're going to be talking about a few more, slightly more advanced concepts in AC generator. Specifically, we're going to talk about AC generator control. And the two most important things that you have to control about AC generators, well, what do we care about on the electric grid? I care that when I plug in my device on a wall outlet, I care that it gives me 120 volts, and I care that it's at 60 hertz AC. I care that it's 60 hertz, and I care that it's 120 volts. That's mainly what I care about when I plug something into a wall outlet. I'm assuming it's at 120 volts, and I'm assuming it's going to give me 60 hertz AC. So the most important things to control about the generator are the voltage and the frequency. So that is specifically what we're going to talk about next time. We'll talk about how you would control a generator's output voltage and how you would control its output frequency. We've started talking about that actually a little bit, believe it or not. Even in problem set number 14 that we talked about at the beginning of class today, we started talking about what could you do to change the output of the generator. But we'll talk in more specifics and again, more real world. We'll talk about how we actually control the output of a generator in the real world in the next class session. So that's going to wrap things up for today. I'll see you next time.